Okay, so you have to go to infinity. Basically, you have to take the electron an infinite distance away from the in this model, an infinite distance away from the nucleus in order for it to be unbound. And this basically is a property of the Coulomb uh, interaction because it acts over infinite range. Okay, it never goes to zero. Okay, and anywhere in between zero separation and infinity, then the energy is less than zero but finite, and that says that the electron is bound to the nucleus. Okay, so basically this says that in this model the electron is always bound to the nucleus, and if it's going in a circular orbit, okay, and the electron can have any energy, okay, it can have any energy in the range from minus infinity to zero, uh, depending on its orbital radius and the orbital speed, the orbital velocity, which corresponds to that particular radius. So again, this doesn't mean that the electron can't. I should say that this doesn't mean that the electron can't be unbound. It just means that if it's following a circular orbit, it if it's falling in one of these circular orbits that's stationary, that is, that has a particular radius, then it is not going to. Then it can't be unbound. Okay. All right. So this is the what comes out of just a simple planetary model. Okay. Doing classical physics, we haven't done anything that's not classical physics yet. And the problems with the planetary model are that this continuous energy spectrum, which I just mentioned, so this the possibility the electron can obtain any energy between minus infinity and zero, does not agree with the discrete emission and absorption spectrum that Bohr and others had observed. Okay, so it's difficult in if you have a continuous energy spectrum for the electrons, it's hard to explain why you'd get these discrete wavelengths, these discrete light frequencies out of hydrogen gas, for example. Okay, and the other problem is that the electron in this model is constantly accelerating. Okay, so when something's going around in a circle, then by definition that means it's accelerating because it's always changing its direction. And classically, a charge which is accelerating radiates. It radiates electromagnetic energy. Okay, so if it's radiating electromagnetic energy continuously as it circles, then it's losing energy. The energy has to go somewhere. So if it's radiating energy, that it takes away energy, basically it takes away kinetic energy, it should slow down. And when it slows down, that means it has to move to a lower and lower orbital radius, and eventually, depending on its rate of radiation, which is related to its acceleration, it should spiral inward and eventually crash into the nucleus, and again where the model breaks down. Okay, so these are the two problems. These are the two most important problems with the simple planetary model that Bohr had proposed. Okay, but he actually had some solutions in mind that would circumvent these problems. In particular, he proposed two postulates. Okay, the first postulate is that the electron orbitals, which we mentioned, are actually not as simple as we've thought of them. Basically, just a classical particle, an electron going around in a circular orbit. They are stationary states somehow, which do not radiate electromagnetic energy. Okay, so somehow these orbitals are, the motion of the electron in these orbitals is such that, or the composition of these orbitals is such that the electrons don't radiate energy because they're stationary, meaning they're not in some sense they're not accelerating. Okay, and the charge is not accelerating. And also the other postulate that he made was that the orbital angular momentum, associated with the electron's orbit around the around the nucleus, is quantized. That is, it can only be integer multiples of our famous and constant h bar, Planck's constant divided by 2 pi.